OpenRefine. So instead of giving you an abstract description of the tool, I'm just going to set this talk on a certain course towards failure by attempting a live demo. And once that has failed, I'm going to move on to the models and try to convince you that they can be useful in some way. Okay, so let's do this. Is it visible? Yeah, it seems to work. Okay, so OpenRefine is an awesome data cleaning tool that is also open source, free as in free speech, and it accepts all sorts of input formats, but I've already created a project to show you how it works. So it works in tables. This is an extract from the RIPE dump, which contains the allocation of IP ranges to institutions. And you don't have to know anything about IPv6 or the policies of allocating these things to institutions, because I don't know anything about that myself. So that's a pretty safe guarantee that it won't be needed. So what sort of things can you do with this software? Well, so this is really the raw data, and we can explore it. So it looks a bit like some spreadsheet software, right? But it's quite different. And the first way you can see how it differs is that it only shows a fraction of the data. You see, you have 100,000 rows, and you're only showing a selection of them. And the reason for that is that in OpenRefine, everything you do on your table is going to be applied uniformly on each row in your table. So you only need to understand the shape of your data set without looking at every single item in it to know what sort of transformations you want to do. So let's give an example of the sort of transformations you can do. So this is the column where I have the IP ranges, and I could use that column to derive the lookup URL for that range so that I can go to the web interface to look up more information about this IP range. So I'm going to take that column and add a column based on this column. And now I have a small expression language, just like things you would have in spreadsheet software, to derive new values from this value. So I'm just going to concatenate some strings to make a URL out of it. So I'm going to call this new column like that, maybe. OK. So you can see it did it for all rows. If I keep browsing, I'm going to have the same things. And now I can view this if I manage to. So now I get more information, right? And I could also store the content of that URL on the table if I want to extract this data and do more things with it. OK? What else can we do? We have this funny status column here where we don't really know what it means. But we can inspect the sort of values it takes by creating what we call a facet. So a facet gives you an overview of all the values you have in a given column. And you can see it's a bit messy, right? Because clearly some of these values mean the same thing. So it's not very well curated. So that's typically the sort of things that you can clean quite easily with this sort of software. So I'm just going to take that column, and I'm going to cluster the values. So this is a set of heuristics to detect potential duplicates with, fingerprints and edit distance, things like that. So in this case, it works fairly well. It's mostly about normalizing the case and adding dashes where needed. So I'm going to validate that. Okay, and now I get a clean set of values on my table. Why on earth am I showing you this? Just because there's a really cool feature in this software, which is the undo redo tab, which really does what it says on the tin. You can go back to any previous state in your project. But there's also this magical extract button here. And what it does is it gives you the ability to represent the operations you've done on your table in some format in JSON. And later on, you can reapply these operations on another data set. So if you get a new version of your dump next year from the same data provider with the same mistakes in the curation, you can do your same process again on your data set. And this is a really popular feature for a lot of people who don't think of themselves as programmers and suddenly realize they can do things intuitively with the user interface and then automate this workflow. Okay? So now this feature isn't quite perfect. Why? Because people use that for all sorts of things. And then, of course, the representation of these workflows in this weird format is not very easy to manipulate. So if you want to adapt maybe the column names because the data provider changed them in the new version of your dump, you will have to go through this JSON file and change these column names. So it's very error-prone. It's not convenient at all. If you just want to interpret a workflow done by someone else, you can't really tell what it does just by looking at it, right? It's very, very opaque. So that's one sort of problem we have with it. Another thing we get often on the mailing list is these sort of messages. Hi, I'm a newbie, and I have this workflow of, say, 6 operations, and I want to undo the one in the middle. How do I do that? And then people say, well, just copy-paste that bit of the JSON and put it back. And that's not convenient at all, of course. So if you think like me and you see this sort of problems, you will agree that this is absolutely crying out for a categorical treatment. You just want these operations to be morphisms in some category and then be able to reason about these by axiomatizing that model and then being able to say whether 2 operations commute, whether 2 workflows are equivalent. And once we have this model, we should be able to let people manipulate these workflows more easily. And hopefully, because category theory gives us this possibility of deriving graphical representations for a model, for the models we have, maybe we could actually take these string diagrams and put them in the graphical interface of this tool. And maybe because these string diagrams are super easy to understand, even if we don't know any category theory, these users could find them useful to manipulate the workflows graphically without having any knowledge of category theory at all. So that's the goal. It's really about taking these string diagrams and making them putting them to use for a lot of people. So let's just do that. How can we model this software in categorical terms? So the data model is very simple. You have tables, which are just sets of rows. Each row is a tuple of column values. And because I told you that these operations run row-wise, independently of the other rows, what an operation is really just a function that takes a tuple of cell values and gives you the new tuple of cell values, potentially longer if you created a new column, or shorter if you collapsed or deleted some columns. So a very simple way to model this is just to say that we're going to take the free Cartesian category on some set of basic data types, and the generators for morphisms are just going to be the operations that are supported by the tool. And that is going to let us represent these operations as morphisms in this Cartesian category. Very simple. So we can get graphical representations for these morphisms just by noticing that a Cartesian category is a symmetric monodal category, so we can reuse these string diagrams and add the copying and discarding morphisms with the required axioms for that. And then we have the algebraic generators that I'm going to draw as white nodes. And these are the basic operations supported by the tool. they can potentially be parameterized by some expressions, as I showed you before. So with this convention, you get that sort of representation for the workflow I've just shown you. So we started with the range column here. We copied it to derive a new column with this operation that concatenated prefixes and suffixes. And we didn't do anything about some columns in the middle. I just drew one, but there were others. And then we did something about the status to normalize it, and that didn't use any other information. And just with this very simple representation, we can already see that these two operations actually commute. Surprise, right? Because they didn't use any common information, so we can run them independently. And if I had actually fetched the content of these URLs here, that would be a really long-running operation for 100,000 rows. So that would be quite useful to know that I can actually do something else on the rest of the columns in the meantime. And at the moment, the tool is extremely naive in that respect. It's completely enabled to reorder any operations. And the scheduling of these operations is also very naive. There's no time sharing at all. It's just sequential execution. So just implementing these IDs would already be quite beneficial for users. What else can you do? Well, you can say that you can also have normal forms for your diagrams that represent workflows. So if you have some combination of algebraic operations, exchanges, copying and discarding morphisms, assuming your operations only have one output leg, you can always rewrite them to this form where you have all the copying and discarding first, then all the exchanges, and then all the algebraic operations. So you can decide if two workflows are equivalent up to these axioms fairly easily. Right, so this is fairly simple. Is it really interesting to use category theory to come up with that? Not really, right? Because these string diagrams are actually just directed acyclic graphs. You don't need to call them string diagrams for that. And they're, of course, already used in a lot of different tools. So if you go to this, for instance, 3D modeling software, you can already compose rendering pipelines graphically with these modules that you connect with wires, right? And I'm sure the people who designed that user interface knew nothing at all about category theory, and they got it perfectly right. So category theory is a bit useless so far. But at least it recovers something that is quite natural for people. But thankfully, I haven't shown you everything OpenRefine can do. So I'm going to show you a second model which contains filters. So what are filters? I'm going to go back to the tool. Let's go back to the main view. So what do we want to do with this data? One thing we could do is try to get mapping from these IP ranges to locations so that we could geolocate users. We would be really evil and track users on the web. So how do we do that? We have these description columns here, which contain the addresses of these institutions. And we could say, well, maybe we want to extract postcodes from these columns. We have postcodes here. So that's going to be an operation that depends on the country, of course, because the format of these postcodes are not always the same. So let's use a facet on this country column. And one thing I can do with facets is click on some options, and that filters the rows which contain this value. And now if I run an operation in this state, it's going to be applied only for these rows. So that gives you a way to do conditional operations. So I'm maybe trying to extract it from this column because it looks like it's got some postcodes in it. So let's take that, and I'm going to add a column based on this column. And now just come up with some regular expression to extract German postcodes. So I've already got one here. And I'm going to create that. And we get the postcodes here. And now if we reset the filter here, the operation didn't run on the other countries, so you can't really see it here because there wasn't any postcode to extract anyway. But the column was told by null values in this case for the rest of the rows. So that lets you, of course, do all sorts of things. You can combine facets together. You can do facets in multiple columns and things like that. And it's quite powerful when you get used to that sort of way of doing things. So how can we model that? I'm sure there's many ways you can do it. And one way I've come up with is just to take the first model we had and generate a new category on top of it. So we generate a free co-Cartesian category on top of it. And this is, of course, a bit hard to read. I'm going to show you in a minute a graphical representation for it. But simply speaking, the objects of this new category are just lists of objects of the first category. So you can think of them as disjunctions of schemas, because the previous objects were table schemas. The morphisms are going to be generated by the operations we had in the first category, plus some filters are going to let us split a table into two parts, depending on some predicate on the rows. So this is what the graphical representation looks like. So because you have two monoidal operations on your objects, they become two-dimensional objects graphically. So an operation is still going to be represented pretty much like before as a Cartesian string diagram in a plane. And then a filter is going to take one sheet, so one table really, is going to split it into two parts. And it does so by looking at a subset of the columns in this table. So these are the ones that are connected to this dot here. And the rest of the columns aren't used to determine if a row goes to the left or to the right. So they just happen to be there, but they're not used for the predicate. So it's really simple to interpret that. You imagine you have a row coming from the top, and the filter looks at some values in that row and determines from that if it should go to the left or to the right sheet. Now you have then the union of two tables, and for that you need them to have the same schema, so the same set of columns. And to get the unit for that union, we have the empty table. For any schema, you can generate the empty table, which doesn't have any row. And of course, we get some axioms to relate these generators. But first, I'm going to show you what the workflow we've just done looks like in this representation. So this is the first part of the workflow we've done. So we had the URL generation and the clustering. And then the filter comes. So the filter takes the country column and takes the German records to the right and the other records to the left. And we take the description column in for the German records, and we extract the postcode from it with this gamma morphism here. And in order to be able to join the two sheets at the end to get one table, on the other side we had this epsilon morphism, which generates these empty values, these null values for so that they have the same schema. Yes?
Why is the morphism represented as a dot on only one of the vertical lines?
So that's because it's only looking at the country column to determine if a row is going to the left or to the right. And you could actually have more wires coming in if maybe you're looking at two coordinates and do a scatterplot facet or things like that. Does this representation make sense to you so far? Yeah. So then let's have a look at the axioms. So a simple one is that if you split the table and then don't do anything, join it back just after that, it's the same as not doing anything. So for this, we notice that in this model, we don't have any order on the rows, right? Because to be able to join two sheets, you need them to not have any order between the rows. So tables are really sets of rows, not lists of rows. If you have one facet and then you apply the same facet to both sides, you can commute the two if you remember to swap the middle sheets afterwards to preserve the ordering. And that works even if the facets use the same columns to select their rows. Then that's where the notation becomes useful. That's where it's important to keep track of what column a facet is using. Because so if you're running two operations on both sides of a filter, you want maybe to just run it once beforehand. But in order to be able to do that, you need to make sure that that operation doesn't modify the column that the filter is working on, because you could change the semantics by doing that. On the other hand, if you have a copying morphism, then you can commute it with a filter even if they use the same column, because it's the same thing. The copying morphism doesn't change the data at all. And the last axiom is about applying the same filter twice. So if you split a data set with the first filter, and then you apply the same filter again on one leg of the data set, that's not extremely useful, because if a row comes in here, satisfies the filter, it has to satisfy the same filter again. So this sheet is never going to get any records coming in. So it's the same thing as just applying the filter once and then having an empty table in the middle. So that's why you get also the symmetric version here. And with these axioms, you actually you can derive a lot of things already. So I can give semantics to this model simply by giving set-valued interpretations for all the generators. So you get a set for each basic data type. Then you interpret an operation as a function on the appropriate sets. And a filter is interpreted as a subset of the type of value it filters on. And if you have this data, then that generates a functor from my model to set, which takes a workflow and interprets it as the function it executes. And with these very simple semantics, you get a completeness theorem, and says that if you have two workflows, then they're going to be equal via the axioms I've shown you, if and only if their interpretation under any evaluation coincides. So in the sense, we axiomatize as much as we could without looking into what the operations actually do. So that's basically all I have so far. I have a few ideas about what to do next. I would be actually really keen to implement some of this in the tool to see if, I'm not sure why this happens, I don't know. Anyway, yeah. I would be quite keen to implement that in the tool. Of course, the tool also lets users break out of the data model sometimes, and that's also one of the reasons why it's quite popular, because sometimes you need to do things that aren't quite row-wise, and that can be done. So how can we use these modeling methods in these sort of cases? Can these visualizations be still useful? Can we still implement that in some way? I hope that users can understand these representations somehow without having to explain too much upfront. And of course, the axiomatization could be improved in many ways, could be more refined and take into account more properties for the operations. And I'm sure you might have some ideas of to do these modeling in different ways, which might actually be more useful. So I'm quite looking forward to hearing your thoughts about that. Thank you. Yes. Yes, so I'm not completely sure, but I think it would be useful to have the two projections So the first projection I showed you where there wasn't any facets, so I think that's fairly simple to understand. And then the other view could be potentially useful to understand the structure of the filtering that you have in your data set. So somehow being able to view these two projections and maybe manipulate them independently, that would probably avoid the need for this 3D representation. And it's true that it can get quite big as soon as you do complicated workflows. Yeah.
We've been loosely joking, but also working on ZX and virtual reality for quite a long time. But again, it is a problem that people develop of it.
Could you repeat that question?
So the question was, are these 3D representations useful? Can they be understood in practice when the workflows get bigger?
Mine's more like a comment than a question, and sort of a summary of the comment is thank you, and that's all. But it's got a bit more content than that. You said, why on earth would you show us Open Refine? And you gave a good answer, right? It was a good case study of doing some categorical analysis of the system and getting some insights and applied category theory. But there's a kind of orthogonal reason for showing this too, which is why I was sitting here so happy that you were showing this. Half the fun and an awful lot of the value in doing applied category theory is in working with real systems or real data. And real data almost always comes dirty. So exactly what Open Refine, I mean, we're mathematicians, right? So we work with idealized things and we prove our theorems with these idealized things. And then I see people say, no, I'm going to apply it, and then get hit with intractable data until you hit it with a system like Open Refine that gives you a chance to clean up the data you've got to get it into that idealized form that we mathematicians prove theorems about. So it's actually really good that this conference got to see that system, and then really nice to do a case study of it.
Yeah, I hope the system can also.
Open Refine is like 15 years old, I think.
Yeah, it's maybe 10 to 15, something like that. Yeah.
Try to reach to the people that develop this thing and inform them about.
So at the moment, it's mostly me developing the thing. So I've become involved in the open source community that develops that, and yes,
Bought the thing somehow and then kind of.
yeah. So it used to be a Google product for a few years, and then they open sourced it, and it's one of the few Google products that end up actually surviving the abandon by Google. So it's a nice story in that sense.
You showed an operation of merging, merging things. So I didn't know if I understand what happens if you. So what happened? Maybe this question doesn't make sense. But what if you have like two columns and both of them have data in the same place, and then you try to merge them?
So what do you mean by merging? Do you mean concatenating or?
You showed a picture of merging.
Yeah, so that was merging of different subsets of rows. So if you have different facets and different filters, you end up with different subsets of rows. And at some point, you might want to consider them as just one subset. So you just take the union of that set, really. That's all it is. Yeah. No, there's, and it requires them to have the same schema, so the same set of columns and same data types.
Have you thought about the problem of like having, I don't even remember what's a column and what's a row, two columns that each are like partially occupied with data. So like this is a column of people's names, this is also a column of people's names.
Yeah.
And then you'd like to merge them.
Yes.
One, and then of course you do have a column.
That's the sort of workflows you could have in Open Refine. You have all sorts of operations for that.
Yeah.
Yeah.
What is actually the definition of facet?
So a facet is a sort of old search engine term that isn't used much anymore, but it's really just the idea of faceted search is about being able to explore the values you have in some search results via these lists of values and number of occurrences, and then drilling down by adding these filters gradually to find the object you're interested in. So it's really these lists of values that you see on the left-hand side and that you can click to filter.
So in the categorical setting, it's just a split?
Yeah, it's the split, basically, yeah.
Any more questions? Yeah.
Since we have time, I have a more technical question. So,
most, but not all of the software we need for ACT shares a common architecture.
Yes.
Where you have a generic graphical front end comparing to a intermediate language, a logical language or or something, which then dispatches to 20% backends. From what you know about OpenRefine, do you think it fits this architecture?
Not at all. At the moment, if you want to really implement these ideas in the core data model, there's a lot of changes to do, and it would also break probably a lot of features, so it's quite involved. But I'm really interested in this idea that we have this common architecture for a lot of tools that would use string diagrams that should show them to users. So in general, you want ideally some sort of maybe library that would do the string diagram manipulations for you, let people manipulate string diagrams, and then propagate back that information to the backend where operations and data is actually stored. And I have no idea how to formulate that. And sadly, I think I wrote my own renderer for these diagrams because the renderers that are around, homotopy.io, Globular, and things like that, are for slightly different diagrams which don't do exactly what I want to do. And it would be really hard to plug in that existing code into the tool. So it seems quite hard to have one generic code that could be reused in many of these applications. But
but it's actually doable. So just to comment on it, Antonin and me, we spoke about this in Japan in the workshop. And then afterwards I couldn't resist to really try and do something. I worked for years with OpenRefine. And yeah, as you know, the code base, like that's not going to really change. But statebox is a kind of this architecture. So it's really, just now it's just patronage, but it's really made to swap out all these things, different algebras, different diagrams, different stuff. So it's really, you can do it, but it will take a while. But yeah, I know at least what kind of architecture you need for it. So I think it's possible, we'll get there.
Yeah, it's going to take time.
So for instance, in particular, the output format you showed with the text, you can generate that, which is sort of doable. That's what I tried to do. So you could say, like, I'm importing from statebox an OpenRefine process. Like, of course, it doesn't do all of the stuff, but I mean, eventually we'll get there.
How much flexibility is there in terms of what you use to define the operations on the columns? So, for instance, can I pull in a Python script or something like that, and other sorts of sort of more sophisticated computations?
Absolutely. So let's go back to the tool. So if I want to, say, do a more complicated extraction on this column, I can choose other expression languages here. So yes, you can plug that and extend it in many ways.
Last question?
About a third way through your talk, you said something. So you showed something that looked a bit like a normal form, where you had your copying of this card.
Yes. Yeah.
And how much work have you put in towards making that an actual normal form or a rewrite system?
So for Cartesian categories, it's fairly simple. So let me go back to that slide. And it's actually pretty well known. I think, well, it's probably folklore. But so to what extent is this a normal form? Well, this is basically a collection of trees of your generators. So they're normal to the extent that you can do exchanges on them. But really, this is just terms, right? So it's easy to identify them. Exchanges represent one permutation, so that's not unique, but you can easily determine if two such morphisms represent the same permutation. And then that can also be normalized by associativity and unitality. And again, you can have exchanges to deform them, but it's really a normal form. But it's a bit lame to show normal forms for Cartesian categories like this, because it's really not a problem people think of in graphical terms, right? Generally, if you want to find normal forms for Cartesian categories, you just get the terms that correspond to the morphism you have, and that makes it really easy to compare. But it was just the first step towards the second model, really.
Okay, in that case, let's stop and get out